Awesome, 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 awesome. So the title of this last talk is Multi-Server PIR with Full Error Detection and Limited Error Correction. And it's by Reo Eriguchi, Kaoru Kurosawa, and Koji Nuida. And Reo will give the talk.
Thank you for your introduction. My name is Reo Eriguchi. Today I talk about the paper entitled Multi-Server PIR with Full Error Detection and Limited Error Correction. First, we introduce private information retrieval, or PIR for short. In this setting, L servers have copies of database A, which consists of n items. For example, we can consider a database of stock prices of n companies. On the other hand, a client has a private index tau, and she wants to retrieve the tau item of the database. In this example, she may be an investor, and that index may represent the name of a company she is interested in. And usually she wants to keep her index private because for an investor, which company she is interested in is sensitive information. So then PIR enables the client to retrieve the item of her choice without revealing any information on that index. And besides the example of stock market, PIR is also used whenever a client is interested in a database distributed among servers. For example, a database stored in a blockchain. And also PIR has been used as a building block for other cryptographic primitives. Now, there is a trivial solution to realize PIR. It's download the whole database. Then the client can locally retrieve the item of her choice. So clearly it's secure because she never reveals her private index. However, its communication cost is proportional to the database size. So this solution is secure but inefficient. So then a line of research to realize a sublinear communication cost is to construct a multi-server PIR in which more than one server is available. First, if there are at least two servers and at most T servers collude, then we can achieve communication cost of n to the T over L, which is sublinear if the coalition size is much smaller than the total number of servers. The second, if there are at least two servers and they do not collude, then we can achieve a much smaller communication cost, which is subpolynomial in the database side. Here we suppose that these PIR schemes assume that all servers are semi-honest. That is, all servers always return correct answers. However, in a real-world situation, this is not the case. For example, servers may be malicious and they try to make the client output an incorrect value. Also, they may return nothing if they are faulty. Finally, we can also consider a situation where servers have inconsistent databases. For example, if a server has an old database, then the client will receive inconsistent answers. So to deal with malicious servers, several security notions have been proposed. First, error correction enables a client to obtain a correct value, even if a part of servers return incorrect answers. Daniel and Stoll proposed a generic construction of error correcting PIR from any regular PIR. Recently, several error correcting PIR schemes with more time efficient algorithms were proposed. However, error correction is a strong security notion, and as a result, it is impossible to achieve when more than half of servers are malicious. So to deal with a larger number of malicious servers, a weaker security notion of list decoding was proposed, which guarantees that a client obtains multiple values, including a correct one. Although it can deal with more than L over 2 errors, there is still a limitation on the number of detectable errors. So then a natural question is whether it is possible to deal with the maximum number of errors if we introduce a much weaker security notion. So now we show our results. We first introduce a new security notion of fully error detecting PIR, which guarantees that with high probability, a client outputs a correct value or the special symbol bot, even if L-1 servers are malicious. Here, this symbol denotes the detection of errors. So if servers return incorrect answers, then client no longer obtains a correct value, but she can learn that the answers she received are inconsistent. So in other words, with high probability, she never outputs an incorrect value. So this is a weaker security notion than error correction and list decoding, but it can be achieved even if the number of errors is the maximum. So next, we show our first technical result is a negative one. We show that there is no efficient solution to realize one fully error detecting PIR, that is a perfect error detection. Specifically, we show that any one fully error detecting PIR requires a communication cost that is linear in the database size. So as a corollary of this result, we can show that the trivial solution, downloading the whole database, is communication optimal. Because a client can detect errors with probability 1 simply by checking the consistency of the downloaded databases. So next, we also show a positive result. We have shown that perfect error detection is impossible. So we allow small but non-zero probability of failure epsilon, and we show that two incomparable 1 minus epsilon fully error detecting PIR schemes. The first one has subpolynomial communication cost that servers are supposed to be non-colluding. The second one has requires higher communication cost, but it still works even if part of the servers collude. As a comparison, we show the best known communication cost of regular PIR with no error detection. In this setting, if servers are non-colluding, the state-of-the-art complexity is a subpolynomial function in the database size. So the difference is only in a factor of log of epsilon inverse. Also, if servers collude, the situation is similar. Finally, we also show that our schemes additionally achieve limited error correction. Although the number of errors must be less than L/2, recall that error correction is possible only if more than half of the servers are honest. So this limited error correction capability is not so bad. So from now on, we explain the technical details of our results. First, we show our impossibility result. Let's consider any one fully error detecting PIR that detects errors with probability 1. And then we show that the communication cost must be at least L times N. So to see this, fix a possible query sent to the first server. Then the answer of the first server is a function of the client's query and a database. So then we can define a function f from the set of databases to a domain of answers. So we will prove that f is injective. As a result, we have that the length of the first server's answer is at least n. So therefore, the total length of answers must be at least L times n. So to see that f is injective, we assume the contrary. That is, the values of f coincide on the two different databases. So let tau be the mismatch position. And let's consider a situation where the first server is honest and the others are malicious. They have a database A and a client has that index tau. So then, first, because of the privacy of PIR, Q1 is actually sent to the first server with non-zero probability. And let's consider an attack in which malicious servers send their messages as if the database was B. So then, on the other hand, the first server honestly behaves. So then, one full error detection guarantees that a client outputs a tau or as a special symbol bot. On the other hand, from the assumption the answer of the first server is equal to the answer it would send if the database was B. So the correctness implies that the client outputs a B tau, so which is a contradiction. So therefore, we have the function f is injected. As a corollary of this our result, we can see that the trivial solution downloading the whole database is communication optimal as long as perfect error detection is concerned. Recall that the trivial scheme in the trivial scheme, the client downloads the L databases, so she can detect errors with the probability 1 simply by checking the consistency of L databases. So this implies a 1 full error detection, and also clearly the communication cost achieves our lower bound L times N. So we can see that the trivial scheme is optimal. So from now on, we explain our construction of fully error detecting PIR schemes. We have shown that perfect error detection is impossible. So from now on, we explain statistical fully error detecting PIR schemes. First, we deal with a situation where servers are non-colluding, and we show that our PIR schemes with subpolynomial communication cost. Before explaining the general case of error servers, we first explained our two-server fully error detecting PIR. That is, there are two servers, and one of the servers is malicious, and a client wants to detect it if that server returns incorrect answers. So our scheme is based on the previous two-server PIR proposed by Deborah and Gopi, which has the currently best known communication cost in this setting. So we modify that scheme so that it realizes full error detection. So now we recall the previous two-server PIR by Deborah and Gopi. In this scheme, a client first encodes her private index as E of tau. Here, E denotes an encoding function based on a matching vector family, but we omit the detailed description here. She then masks her encoding with a random vector R and sends them to servers. In turn, as each server returns a value of polynomial f and on some point x1 or x2, along with the derivative on that point. Here, f is a sparse polynomial with only 4 monomials, and the constant term is the A of tau, which is the item of the client choice. So then she has obtained 4 constraints, 2 values and 2 derivatives on the function f. So therefore, she can recover the interpolating polynomial f from its values and derivatives. So finally, she can output the correct value simply by looking at the constant term. So it indeed satisfies correctness, but it doesn't work if one of the servers is malicious. For example, suppose that the second server is malicious and it modifies its answers by adding some errors. So then when reconstructing an interpolating polynomial, the client will use these modified values and derivatives. So then the second server can make the client compute an arbitrarily polynomial. And as a result, the second server can arbitrarily modify the client's output. So the client has no way to detect errors. So to solve that problem, we make use of the Tompoval technique, which was originally proposed to make Shamir's secret sharing scheme error detecting. So that is, it is possible to detect detect errors if some of shares are modified when reconstructing a secret. Recall that in a standard Shamir scheme, each share is a value of a function f on some point. Their key idea is to define shares as values of a polynomial f on random points. So their reconstruction algorithm is similar to the standard scheme. So that is, the client when reconstructing a secret, the client collects shares, and first she computes the interpolating polynomial f from these values, and outputs its constant term. So to see why it realizes error detection, suppose that the first and the second shares are modified. Then in the standard Shamir scheme, the client will compute an incorrect polynomial described by this Redger. And as a result, she will output the incorrect secret without detecting the errors. However, in the Tompoval scheme, evaluation points are randomly chosen and they are unknown to the adversary. So therefore, the curve computed by the client is disturbed by this additional randomness. So in particular, its value at 0 is an almost random value. So with a high probability, it will be out of range. For example, it will take an extremely large value. So in summary, if a secret she computes is invalid, then she can learn that the sum of shares are modified. So she outputs bot. So our high-level idea is to apply the Tompoval technique to the previous two-server PIR scheme. Specifically, in our scheme, the client adds some additional randomness to her query. That is instead of simply masking her encoding with a random vector R, she adds a random vector multiplied by this additional random element. So then we can show that if servers are honest, their answers are values and derivatives of a polynomial f on random points. So an important feature is that this additional randomness is unknown to servers. So the Tompoval technique still works in this case. So now to obtain a data item, as in the previous construction, she first recovers the interpolating polynomial f from its values and derivatives. If servers are honest, then she will output the correct value, which is either of 0 or 1. Suppose that the second server modifies answers by adding some errors. Then in the previous scheme, the client will compute an incorrect polynomial described by this Redger. And as a result, she will output an incorrect value without detecting the errors. However, in our scheme, the evaluation points are randomly chosen and they are unknown to servers. So a malicious server cannot tell which points are used in the reconstruction. So therefore, even if the second server adds the same errors to its answers, now the recovered polynomial is disturbed by this additional randomness. So in particular, its value at 0 is an almost random value. So we then conclude that with high probability, it will be out of range. So she can detect inconsistency in this case. So while our construction may seem to be a simple application of the Tompoval technique, our technical contribution is generalizing the security analysis of the Tompoval technique to the setting of Hermite interpolation, which uses derivatives in addition to values to recover a polynomial. Furthermore, because we have to choose alphas from a sufficiently large domain to make the probability of failure negligible, so we need to rearrange the parameters of the underlying matching vector family. So we construct a suitable new family of matching vector families. So now we go to the next step. We have shown our two-server 2D error detection PIR. To construct an L-server scheme, we propose a generic transformation which increases the number of detectable errors and also adds error correction capability. Here we focus on a simple case of transformations from 2 to L servers. In this case, our transformation is very simple. The resulting scheme simply executes independent instances of the previous two-server scheme for all pairs of two servers. Then, if the client gets the same values in all instances, then she outputs that value. Otherwise, she can detect that there are there are some modified answers, so she outputs the bot. As to quantify the success probability, we simply assume that there are 3 servers and the second and third servers are malicious. Then, in instances involving the first server, which is honest, a client can detect errors with probability at least 1 minus epsilon. On the other hand, because we assume that servers are non-colluding, so these instances are independent. So therefore, the probability that malicious servers can successfully make a client output an incorrect value is upper bounded by epsilon to L minus 1. So therefore, our resulting scheme is fully error detecting for smaller probability of failure. Now we can also see that our resulting scheme satisfies a limited error correction. We observe that if all servers are honest, a client can compute the correct value from any 2 out of L servers. So this property is called 2 out of L robustness, which was originally introduced by Demo and Stoll. They also show that the 2 out of L robustness implies L over 2 minus 1 error correction for free. So therefore, our scheme satisfying this robustness trivially satisfies limited error correction. So finally, after applying our transformation, the resulting communication cost is increases by L squared times. So because we have to run L choose 2 instances of the previous 2 server scheme. On the other hand, the probability of failure decreases. So therefore, the final communication cost is only linear in the data and the number of servers. So we have also shown that our scheme satisfies error correction. So now we move on. We move on to the second scheme, but time is it's almost time, so we skip this part. So we summarize. Finally, we summarize this talk. We first introduce a new security notion of fully error detecting PIR to deal with maximum number of errors. So our first negative result is we show that there is no efficient solution to realize one fully error detecting PIR. Specifically, we show that any one fully error detecting PIR requires communication cost that is linear in the database size. We also show positive results. We have shown that perfect error detection is possible. So we allow small but non-zero probability of failure epsilon, and we show that there are 2 incomparable statistical fully error detecting PIR schemes. This is the end of my presentation. That's all. Thank you.
Any questions? So I had one question about
Sure.
The positive results. So is there any hope? I guess you, as you mentioned, had to do kind of a new analysis of this 2 server PIR scheme, the Eriguchi scheme, to get your result. Is there any hope for some kind of black box transformation that is error detection?
It's a possible future work. So our construction is specialized for the previous scheme. So possible future work is that to propose a generic construction of error detecting PIR from any regular PIR. Yeah.
Other questions? Maybe people are ready for the coffee break. All right, so let's thank Reo again, and be back at 11.
Thank you.